Okay, we'll get started. So Tuesday we started talking about Lewis structures. We made a few points. We're just going to make those points one more time to make sure that hopefully they set in. And then we're going to use them to evaluate a few different molecules. So what I want you guys to remember is this. In chemistry, we're always using different mechanisms of approximation. When we did our analysis of redox numbers, the redox numbers didn't fully communicate where electrons were located in the molecules, but we used an approximation to decide where, or to estimate where those electrons were in molecules. When we build Lewis structures, we're doing the same thing. We're making an approximation. We're generating structures based on a set of rules that kind of describe electron distributions around molecules. Those structures are not perfect representations of electron density in the molecules. What we're going to see is oftentimes there are multiple Lewis structures available for a molecule. In those cases, oftentimes the truth is that the true electron distribution in the molecule is something of a weighted average of all of the different Lewis structures. And we'll talk about that as we work through some examples. But just keep in mind that what we're doing is we're estimating electron distributions across these molecules using Lewis structures. Something that I want to remind us of is this. When we did redox numbers, oxidation numbers, we assumed that, so we make several assumptions here. We assume for redox numbers that the electron goes to the most electronegative species. And so if we have one atom that's sitting in proximity to another atom that it's more electronegative than that, we assume that the more electronegative species wins the entire electron. When we count octets, or valence electrons, we make another assumption, and that is that when counting valence electrons, both electrons get counted towards the atom's valence. So if we have, water's always easy, if we have a water molecule, and we're calculating to determine which of these atoms has filled valence shells, in this case, the two electrons in the oxygen-hydrogen bond get counted towards hydrogen's valence, and they get counted towards oxygen's valence. So we're counting valence, we're just assuming that there's a certain number of electrons that can fit around the shell, and that bonded electrons count towards the valence of both atom types. So that's another assumption that we make. So for valence, counting valence, bonded electrons count towards both atoms. Okay, and when we do the formal charge calculation, we make an entirely different assumption. Now, formal charges are what we're going to use to evaluate these Lewis structures. For formal charges, we assume that the electrons are split evenly. Bonded electrons are shared or split evenly. So for instance, if we were counting the formal charge of this oxygen here, it gets both of those electrons in the lone pairs plus half of all of these bonding electrons in these single bonds. So if we have 4 electrons in bonding, 2 of those get counted towards oxygen. If you ran that calculation, you would find out that oxygen has a 0 formal charge. Might be nice to stick the equation for formal charges up here real quick. The formal charge is equal to the number of valence electrons in the neutral atom minus the sum of the lone pairs plus 1/2 of the bonding electrons. Okay? And what that formal charge calculation does is it allows us to kind of approximate the relative amount of charge that the atom has in our Lewis structure versus the amount of charge that it comes with in the neutral atom. Okay, so these are the assumptions, or some of the assumptions we have to remember. The other thing that you need to remember is that when we're building Lewis structures, we're basically saying that if you take a bunch of atoms and you stick them together and you let them make a molecule, they're going to share only their valence electrons. And we said that that was because the core electrons that are tucked into deep subshells are so tight in the nucleus and the nuclear force is so strong on them that they don't really get to be shared amongst the different atoms. The valence electrons, though, with smaller nuclear forces binding them, are more available for sharing. And so when we build Lewis structures, we're saying we're going to get a bunch of atoms together, we're going to count up the total number of valence electrons that are available, and we're going to proportion them off. One thing you need to remember, for species that have a charge, there will be extra or fewer valence electrons depending on what that charge is. If you have a negative ion, a polyatomic ion that's negatively charged, then you're going to have to bring in extra valence electrons to account for the charge on the ion. If the ion's got a negative charge, then you've got more electrons than protons, right? If you have an ion that's positively charged, then you're going to have to subtract valence electrons for a positively charged ion. We'll see some examples of this in a second. Let's say a little bit about formal charge. In a second, we're going to get a chance to use formal charge to evaluate different structures for their quality. And here's the story. I told you guys, well, first of all, any negative formal charge should show up in your Lewis structure on most electronegative atom types. So this makes sense. If you get a bunch of atoms together and you allow them to share valence electrons, whichever atom type is the most electronegative is going to have the greatest tendency to pull those electrons towards itself. And so if you have a situation where you have to create a Lewis structure that has negative formal charge, you're going to want to make sure that that goes on the most electronegative atom type. Also, if you have a Lewis structure that has positive formal charge, that formal charge should probably go on the species that has the least electronegativity, right? It's going to have the least pull on electrons. So when we evaluate our Lewis structures, we'll be looking to see that the formal charge is on the appropriate atom types. When you go through your rules for constructing these Lewis structures, and this is in your lab manual. You can read it out of the lab manual as well as hearing it from me. You're going to be told that having formal charge is in general a bad thing, and that you want to try to select whichever structures have the least amount of formal charge. So here's what this means. Say we're taking a neutral molecule. You got a neutral molecule that has no charge. And we have a structure, let's just say it's made of two atoms. We have two different structures. One places a 0 formal charge on that atom and a 0 formal charge on that atom. Another structure, these are just generic atoms. Another structure that we have, let's say that it puts a positive formal charge on one atom and a negative formal charge on the other atom. And we're asked to evaluate which of those structures is most realistic. Remember at the beginning of the class when I told you that to separate charge from each other, you you got to put energy in. Take a positive charge and a negative charge. We want to separate them, we got to put energy in. Well, that holds true for molecules as well. If you have a molecule that has charge separation across it, that represents a relatively high energy state, right? It takes energy to move positive charge and negative charge away from each other, period. And so if we have two structures that are available for our molecule, a neutral molecule, the one that has the least amount of separation of charge is the one that's the lowest energy species and is therefore most likely to occur in nature. Okay? And so we're going to be learning to look at molecules and decide whether or not the formal charge is on the appropriate atom type, or whether or not the formal charge is minimized. We're going to try to get rid of formal charge if we can. If we can't, we're going to try to make sure that the formal charge goes on the most electronegative atom. Let's give you another example discussing formal charge. So this is really generic. Let's say that we have some linear molecule, and you got a couple of different Lewis structures that are available to draw on this molecule. Let's say that one of them places a positive formal charge at a far end species, and the other one sticks a negative formal charge at the other end. Say you have this structure, but you've got another one available where the positive formal charge is located here, and the negative formal charge is located there, in these center atoms. If you were to evaluate these, you'd be expected to identify this bottom molecule as being the lowest energy, or the more appropriate structure. And here's why. It all goes back to the charge thing. It takes more energy to separate charges by a large distance than it does to separate them by a small distance. And so a structure that shows charge separation spread way across a molecule is actually higher energy and less likely in nature than a structure that shows charge separation positioned close together on a molecule.
For the first example, is that the 0, 0?
Yeah, I'm saying that, so if you have a molecule that has just two atoms, and the Lewis structure that you draw for it can show zero formal charge on both atoms, that's going to be a lower energy and more stable or more naturally likely species than one that actually has charge separated. So if you can build a Lewis structure that has zero formal charge, good news, you're in a low energy species. If you can't, then you have to try to make sure that the formal charge goes on the appropriate atom types, and you have to try to minimize the distance that those charges are separated from each other across the molecule.
Can you explain the last sentence? I can't understand.
Any negative formal charge belongs on the most electronegative atom. So let's say you have a molecule that's got a fluorine and an oxygen, and you have a choice to put a negative formal charge on a fluorine or a negative formal charge on an oxygen. Well, because the fluorine is more electronegative than oxygen, the structure with the negative formal charge on the fluorine would tend to be the more realistic structure. Again, we're just choosing the best structure. In truth, none of these structures represents the true electron density across the molecule. We're just making approximations. But we can learn from these approximations, and we can take all of the structures and sum them together and build something that looks very much like the true electron density of the molecule. So a real quick review. Set of rules that we're going to go by. I encourage you to dig up this protocol while you're doing your homeworks and follow the directions as you do the problems in homework. Number one, add up all the electrons. Take all of the atoms, count their valence electrons, and the number of valence electrons that you come up with after you've accounted for any charge on the molecule is the number of electrons that have to be shared. So count the valence electrons, find out how many valence electrons it is that we're dealing with that we have to spread out. The second thing that we're going to do, which can be very difficult in some circumstances if you don't already know the structure, is we're going to try to determine, and this is in number 2, kind of the rough geometrical arrangement of the atoms. In the problems that you get in this class, it's going to be safe to assume that the least electronegative species is in the center, and that the more electronegative species are attacking it, going after it for electrons. Not always that simple. There are some molecules that you wouldn't be able to, probably off the top of your head, just come up with the exact three-dimensional orientations of the atoms with respect to one another. So we count our valence electrons, we figure out an approximate geometry, and now we're going to go in and we're going to start giving these electrons away. The first thing that we're going to do is we're going to spend electrons as bonds between atoms. In a molecule, atoms are held together by electron density that exists between them, right? You have two atoms that are attracted to each other. It's because electrons are sitting in between them, and both of those positive atoms are going after those electrons, and they kind of come together in doing so. When we build our Lewis structures, we're always going to draw just a single bond between two atoms, and that single bond we're going to assume is two electrons. Now this gets back to where this is an approximation. In truth, in the molecular system, you might have a quote-unquote covalent bond that doesn't have a full two electrons sitting between the two atoms. It might have a little bit more than two electrons, it might have a little bit less than two electrons. But we make the approximation when we draw that single dash, and when we evaluate our Lewis structures, that each of those bonds represents two shared electrons. Again, it's an approximation, it's not exactly true, but we're going to do it to build these structures. All right? So now we've tied all of the atoms together by bonds, and we've still got valence electrons that need to be divided amongst the available atoms. Your notes tell you to start taking the kind of perimeter atoms and give them lone pair electrons until they fill their valence shells first. And the reason for that is that if you put the least electronegative atom in the center, then the peripheral atoms are the ones that are more electronegative, and they're going to get priority on the electrons that you're distributing. So you give those electrons away as lone pairs to the more electronegative atoms first, and then after all of the electrons, or all of the valence conditions of the peripheral atoms have been satisfied, you check to see whether or not the central atom has its electronic requirements satisfied. If it doesn't, and you still have electrons left over, you'll start giving those electrons to the central atom or the least electronegative atom last. If you don't yet have, or if you don't have any electrons remaining, and the central atom still does not have an octet of electrons, then you're going to start assuming that what you assign to peripheral atoms as lone pairs are not in fact lone pairs, but are going to be bonding pairs due to bonds that form as that central atom tries to fill its valence shell. And so we begin the process of moving lone pair electrons in towards into bonding positions to the central atom in an attempt to show the central atom with a filled valence shell. All right? And then at that act, well, actually, I can move this down a little bit. Number 5, moving those lone pair electrons into bonding positions. In any given molecular setup, that could result in multiple Lewis structures generated. And it will, in many situations, result in different possible Lewis structures. We'll go through some examples of that. If that's the case, and you have several different Lewis structures that are all valid in terms of distribution of electrons and filling of valence shells of the atoms in the molecule, then you have to go ahead and start to weigh the different possible structures and see which one is the most realistic based on formal charge. And that's pretty much it. Count the electrons, establish geometries, distribute electrons as bonds, distribute electrons as lone pairs, satisfy the octet of the central atom, and then weigh all of the different Lewis structures using formal charge analysis. All right? So, practice makes perfect. Let's do some practice. going to build CO2, carbon dioxide. How many valence electrons do we have? Carbon dioxide, you got one carbon in there, it's got 4 electrons in its valence, you got 2 oxygens, those got 2 apiece, or sorry, 12, 6 apiece for 12. So 12 plus 4 is 16. Yeah? 16 valence electrons in that CO2 molecule. So that means that when those 3 atoms come together, an oxygen, or 2 oxygens and a carbon, you're going to have to distribute 16 electrons around the molecule. So notice that it's not charged, so we don't have to adjust the number of electrons for positive or negative charge. First thing we do, we're going to pick the least electronegative atom and stick it in the center. That's going to be our carbon, right? And we'll put the oxygens at surrounding positions. They'll approach at either side of that carbon. And start distributing electrons as bonds. So we have 2 single bonds that would be required to bond the carbons, or the carbon to the 2 oxygens. 2 electrons in this bond, 2 electrons in that bond. So -4 bonding electrons, we'll call it. We now have 12 electrons left that still need to be distributed. All right? The rule is, give them to the most electronegative species first, and if there's still some remaining, we'll give them to the central atom. So we'll go 1, 2, 3, 4, 5, 6. At this point, oxygen has its octet, or has its 8 electrons in its valence shell. We'll stick 1, 2, 3, 4, 5, 6 on that oxygen. At that point, this oxygen has 8 electrons in its valence shell. All right? So our oxygens they have their valence requirement satisfied. We have to pay attention to our electron count. We just spent 12 electrons on those lone pairs of the hydrogens, so we have no more electrons left to distribute across that species. Here's the problem. This carbon, as we've shown it here, does not have a filled valence. It doesn't have 8 electrons in its valence. Carbon likes to have 8 electrons in its valence shell. And so this is not a very good representation of the electron density in this molecule. In truth, that carbon is going to want more electrons than we're showing it with. And so what we're going to do is we're going to start moving these lone pair electrons into bonding positions. And we're going to see where it gets us. Okay, so let's do this one first. We get rid of that, we get rid of these 2 electrons, and we stick them right here. That gives us this species. Not have an octet of electrons around that central carbon. How many electrons do we show in carbon's valence in that structure? 6, because each of the bonds counts towards the atom's valence. So that structure right there displays only 6 electrons in carbon's valence. And so what we're going to need to do at this point is take another set of lone pairs and move them in towards bonds with the carbon. Now what I want you to notice is that there's 2 ways that we could do this. 2 different ways that we could draw a Lewis structure from here by moving lone pairs into bonding positions. We could take a lone pair from this oxygen and move it into a bonding position in carbon. Perfectly legal in terms of creation of Lewis structures. Or we could take one of the lone pairs from this oxygen and move it into bonding positions. Let's watch what happens. Let's do it with this lone pair first. This oxygen. We'll have carbon in the center. We'll have a double bond to that oxygen. And we'll have a double bond to that oxygen. Now, if you do the count of valence electrons, both those oxygens have their octets, as does the carbon. So thumbs up in terms of everybody is electrically satisfied. Yeah? We didn't have to do it that way though. We had a lone pair sitting on this oxygen. So we could have moved that lone pair into a bonding position. If we'd done that, we would have this structure. Now we've got a triple bond between this carbon and this oxygen. We've got a single bond between this carbon and this oxygen. Now, this structure satisfies everyone's gibbons. This oxygen feels like it's got an octet. This oxygen feels like it's got an octet, as does this carbon. And so based on just satisfying everybody's octet condition, both of these structures do the trick. The question is, which structure is most representative of electron density in the molecule? That's where we have to go into formal charge calculations. Once we do the formal charge calculations on this, it'll become very clear which structure is the best. We'll do this one first. So these two oxygens, they're showing the same exact bonds, or same exact number of lone pairs and bonds to carbon. So their formal charge is going to be identical. Formal charge on that oxygen is the number of electrons in its neutral atom, which is 6e minus again the sum of the lone pairs plus half of the bonding electrons. Well, it's got 4 lone pairs, or sorry, 2 lone pairs, but 4 electrons in the form of lone pairs, right? So we'll say 4e minus for lone pairs, plus we've got 2 bonds, and remember for formal charge, we assume that all those electrons are split evenly. And so if there's 4 electrons, 4 shared electrons between this oxygen and the carbon, we're going to assign 2 of them to the oxygen. So that's 1/2 of 4 bonding electrons. 1/2 of 4 is 2. This is basically 6 minus 6 is equal to 0. Both of these oxygens have a 0 formal charge. Brackets across that. Yeah?
6.
Oxygen, how many valence in oxygen, or how many valence electrons in oxygen's outside shell?
Per oxygen.
Yeah. In the neutral atom, oxygen shows up with 6 electrons in its valence, right? And so the formal charge calculation is a comparison of electrons in the neutral atom, valence electrons in the neutral atom versus valence electrons displayed in our Lewis structure.
So you only do it for one.
You do it for all of them.
Do it for a single one.
Yeah. Just like we did with oxidation numbers, you're gonna assign formal charge to every atom in the molecule.
But how do we get the numbers in the bracket? 4e minus.
So it's right here. The formal charge is equal to the number of valence electrons in the neutral atom minus the sum of the lone pair electrons. So 2 times the number of lone pairs, or the total number of lone pair electrons, plus half of the bonding electrons. So you count all of the lone pairs towards that atom, and you count half of the bonding electrons towards the atom. You calculate a difference.
So you don't do anything with carbon?
What's that?
You don't do anything with carbon?
No, we're getting there. I just got stopped a couple times, so I didn't get a chance to get to carbon yet. Okay, so let's do the formal charge calculation for the carbon. Carbon normally comes with 4 electrons in its valence. It doesn't have any lone pairs, so we'll say 0 on the lone pairs, but we're going to give it half of the bonding electrons, and there are 8 bonding electrons. So if there's 8 bonding electrons that carbon is sharing, it's going to get credited with half of those. That's 4. 4 minus 4 is 0. 0 formal charge on that. This Lewis structure right here shows no separation of charge across the molecule. It's showing the oxygens with a 0 formal charge, and it's showing the carbon with a 0 formal charge. Now let's do that same calculation over here. I'll do it in a different color. We'll do the formal charge calculation on this structure. Your oxygen normally comes with 6 electrons. We've got 2 in the form of lone pairs. So subtract from that 2 plus half of the bonding electrons. And the bonding electrons, there's 3 single bonds. So that's 6 electrons total. We give half of those to the oxygen. Half of 6 is 3. And so this is 6 minus 5 is equal to 1. We're going to call this guy plus 1.